Hello and welcome to the technical demonstration of the SPRAYai smart pesticide spraying system. Today I'm going to go over the SPRAYai system, what it is, how it works, and how it can benefit existing agricultural businesses. The Navi from Unmanned is an autonomous agricultural robot designed to assist fruit pickers by automating simple manual tasks and improving efficiency for farmers and growers. The brief, which SPRAYai stemmed from, was to design a smart trailer which provides additional functionality to a small, autonomous off-road vehicle. After a broad investigation into a range of possible focus areas, I landed upon crop spraying. Almost 17,000 metric tons of pesticide were applied to UK crops in 2016. For many crops, pesticide usage is ubiquitous and a requirement to ensure acceptable returns every season. Many crops are treated several times over before harvest, potatoes being one of the most sprayed crops, with a field being treated 32 times on average. By optimizing the spraying process and reducing pesticide usage, numerous benefits could be realized, including economic benefits to the farmer, environmental and health benefits, or improved public image. The problem, reduced to its simplest form, is to only spray when necessary to do so. Pesticide sprayed between rows of crops or onto already healthy plants is wasted. UK agricultural schemes prohibit prophylactic or preventative spraying and instead require farmers to regularly monitor their crops and only spray if a disease has already been identified. By automating the spraying system to only target known pests, a reduction in pesticide usage, as well as a reduction in labour requirements, can be realised. However, a major challenge in achieving this lies in the broad range of crops grown in the UK. Spraying a field of wheat requires different processes, equipment, and materials to a row of raspberries. By grouping similar crops, a solution can be widely adaptable for a range of different scenarios. I functionally decomposed the concept to allow further understanding of the requirements of a smart pesticide system. Although initial plans were to complete a full system prototype, the UK lockdown compelled a distillation of the project, focusing in on the core challenges of the system and leaving aspects which have already been explored in detail commercially, such as pesticide storage, spray patterns, and traversal over fields and crops. This left plant detection and accurate spraying of pesticides. These can be achieved in one of two ways: green versus brown analysis, where the system can distinguish between plants which require spraying and other things which don't, such as bare soil, tarps, or agricultural equipment. Or green versus green analysis, where the system can distinguish between wanted and unwanted plants, spraying only weeds, infected crops, or crops showing symptoms of preventable diseases. At the most basic level, proximity can be used to detect what should and shouldn't be sprayed. Crops are generally closer to the spray nozzle than unwanted background objects. However, this primitive technique quickly falls down with more complex environments and is low accuracy even in optimal conditions. Color segmentation using visible light cameras, or even temperature segmentation using infrared cameras, would provide a more accurate sensing method. However, this is a very specific and fragile solution. Different crops, foreign objects, and even environmental conditions will inhibit or even stop the system functioning entirely. This leads on to more complex technologies available: digital image processing and computer vision. A major benefit to selecting computer vision as the crop detection method is that it can be performed with a standard RGB camera. The software is relatively independent from the mechanical design and electrical components, which turns the concept from a hardware-based product as originally envisioned into a software-based product. A considerable benefit to this method is that improvements and changes to the product can be made well into the product's lifecycle through over-the-air updates in a similar manner to Tesla and their autopilot system. Although existing models are available, none satisfy the bespoke requirements of a smart pesticide spray system, such as detection of specific weeds or plants. Therefore, I needed to train a custom model. Although I researched training semantic segmentation models, the main focus was placed on object detection due to its good trade-off between network output detail and computational intensity. Furthermore, sources revealed the importance of utilizing transfer learning to train custom models. This is a process whereby an existing recognition network is extended by training on a small custom image dataset, typically requiring hundreds or thousands of test images, as opposed to millions of images required to train a reliable network from scratch. At this point, I needed to make a decision regarding the training dataset. Due to the lockdown, access to farms or fields was severely limited. As a result, training a network to spray rows of strawberries or fields of potatoes was no longer feasible. Instead, the system was focused to detect and spray dandelions. As a common garden weed, they are widespread and unwanted, but more importantly, a dataset trained and working on dandelions can easily be retrained and switched to work on a completely different type of crop. Dandelions act as a feasibility stage gate to validate the system concept. Creating a dataset is often done manually by taking photos of the object to detect and tediously outlining all instances of the object for every single image. However, for greatly improved efficiency in the training process, I produced a synthetic dataset comprising of random seed-generated renders of dandelions in a variety of environmental conditions. This allowed the creation of several thousand training images in just a few hours, where a real dataset could take days or weeks to correctly annotate. Now for the tricky bit. The first model was based on a region-based convolutional neural network, specifically Mask RCNN from Matterport. Loading the synthetic dataset, customizing training parameters to match, and running for 80 epochs, problems were quickly identified. Dandelions were missed or detected multiple times, and the bounding boxes were not representative of the location of the plant. Possible issues could include overfitting of the model or a bad dataset. It was quickly realized that the dataset format was encompassing all plants in the image as one, whereas the network expected each dandelion to be identified as a separate object. Writing a script to separate disconnected regions, re-encoding the images, and converting back to the required training format produces a more suitable dataset. However, retraining the model produced further degraded results from the initial model. To optimize project time, I went back to the fundamentals. Mask RCNN is highly capable, but is several years old, and with the pace of machine learning evolution, I sought a more current solution. I discovered Detectron 2, a branch of RCNN by Facebook Research designed for state-of-the-art object detection. In addition to being continually updated, other improvements include greatly improved detection accuracy, inference time, and training speed. Training on my custom dataset took a fraction of the time the previous models took, and initial outputs were incredibly promising, with visual inspection indicating the model was much more accurate than the prior networks. This was confirmed when looking through the training statistics, which showed accuracy rising to over 70% and false negatives falling to under 30%. Further refinement brought accuracy to around 80%, and it was time to deploy. So far, the networks were running on dedicated machine learning servers, which provide performance far greater than a compact device suitable for running the prototype. An NVIDIA Jetson was selected for deployment. It's a single-board computer, similar to the Raspberry Pi, but with dedicated CUDA cores, which are multitudes more powerful than an equivalent CPU. However, after converting and serializing the model to maximize performance, inference time could take up to 70 seconds per frame. As the device needs to be near real-time, this was not acceptable. This is where I realized a mistake in all my efforts up to this point. All the frameworks I had been using were based off an RCNN architecture or derivative. This architecture is designed to be accurate, and although fast implementations are available, it made more sense to switch to an architecture designed from the ground up for speed. You only look once, or YOLO architecture, is built to be fast. I converted my custom dataset to the new required format, configured the training parameters, and trained the new model. Accuracy was great, and performance was around 70 times faster than the Detectron 2 model. Containerizing and building into a Python Flask-based API server brought the inference time down an extra 30% to around 700 milliseconds per frame. Switching to a CUDA-based container for the Jetson reduced time further to under 200 milliseconds per frame. Further iterations, switching to a more powerful Jetson Xavier, compiling the architecture for half precision, and converting the model to utilize dedicated tensor machine learning cores brought inference down to 43 milliseconds, allowing around 23 FPS of real-time plant detection. So now you know how it works, I would like to showcase the physical prototype while explaining the remaining mechanical and user interaction design aspects. Here, the sprayer is set up behind the Navi, However, each spray box is designed from the ground up to be modular and highly flexible to adapt to any spraying environment. 2 boxes on the back of an ATV or autonomous robot function just as well as a 120-foot spray boom with 30 spray boxes. It can even be adapted in situ. Just plug in a new box and it's already linked in with the existing system using HTTP auto host discovery and WebSocket communication. Each box uses a linkage-based design system for actuating the spray nozzle. This allows the required servos, local processing computers, microcontrollers, and camera system to be kept separate from all pesticide, meaning backspray or leaking hoses are not a concern. The final device would be ingress protection rated to at least 65, enabling further protection. Each box contained its own processing capabilities. This is not used for AI inference, but instead to capture and track continuously while in operation. This allows the whole system to move in the time between the initial frame is captured and inference is completed tens of milliseconds later. This uses a highly performant Lucas-Kande optical flow algorithm, which resultantly accounts for translation or rotation of the box in any direction. A custom PCB condenses circuitry required down into a compact add-on board. This includes communication facilities between the microprocessor and microcontroller for hardware control, status LEDs, MOSFET control of the spray solenoid valve, and power distribution. All of this design stemmed from previous iterations, including the first functional prototype, which allowed me to validate the code and concept I had up to that point, after it successfully identified and attempted to target dandelions. Using this, I had identified the main focus areas for improvement to the final design, including changes to the spray nozzle actuation and power systems. Each Jetson acts as the control center, facilitating communication between every spray nozzle over a network and control functions from the user. A simple web UI is used, allowing the user to connect to the device's wireless network on a laptop or tablet and configure the device using a standard web browser. Settings are automatically updated and distributed across the spray network instantly, meaning live alterations can be made while spraying to fine-tune parameters. A status overview of the system is clearly available, as well as the ability to download logs from disconnected spray boxes for debugging. I can start or stop spraying manually here in the UI, but the system design allows for simple webhooks to be defined for any function, meaning custom physical control pads can be integrated specifically to a user's requirements, or communication with an existing agricultural system, such as John Deere Precision AG, is also possible. Again, the connected nature of the device allows communication with external tools also. By adding an IoT SIM plan, all spraying metrics can be periodically pushed to a cloud platform such as OneSoil, where spray coverage and recent performance can all be monitored from anywhere in the world. Finally, all the systems running are designed for simple deployment in production. A software deployment tool called Ansible enables me to take a brand new Jetson or other supported single-board computer with a fresh Linux installation, and in a couple of console commands have the SPRAYai system set up and running in a matter of minutes.